Hello, everyone. Thanks for coming to this talk, and thanks to the organizer, Dr. Yu, and other organizers for the invitation. It's really a great pleasure to share some of our recent works on discovering hierarchical organization brain architecture with deep learning. So let's start with the background. We use fMRI data to model human brain networks and try to discover the organizational architecture of the brain. So traditionally, there have been quite a few very commonly used approach to model fMRI data. For example, GLM, general linear model. So let's look at the basic idea of GLM. So we have the baseline in green and the stimulus in red. And typically people have baseline stimulus, and repeatedly across the time axis. So based on this repeated pattern, we are going to use a general linear model to feed this stimulus curve to the fMRI time series, extract from the volumes of the brain. So typically we have an overlay of the time series and the GM fit after the hemodynamic convolution. So if the fit is very well, so we say this voxel is activated. Otherwise, it's not activated. So of course, there are many techniques to deal with the statistic and the thresholding, so that we can detect the activated voxels. So this is a very classical but a very simplified model to analyze fMRI time series. Okay. Another commonly used approach is called ICA, independent component analysis. So the basic idea is here, we put the fMRI volume in the space, and then we put a time series over here. So we have a two-dimensional matrix. One represents the spatial location, another representing the temporal time point. So we decompose the input matrix into two components. One is represented by A, another represented by S, which is called time series. So typically we say this is the spatial map of the brain networks, okay? And the source has the source localization typically also localize the identify the time series. Sometimes we call dependent component. The basic idea is to assume different components are independent as possible. So they have the multiplication between the source signals and the spatial maps. So that's how we decompose the original input fMRI time series data into brain networks with both temporal activities and spatial distributions. So this is also very commonly used in the fMRI field. So, but more commonly used in the resting state fMRI time series analysis. So in recent years, my group has been working on called sparse coding or sparse diction learning and sparse coding to model fMRI time series. So our idea is like this. We put the input time series into a giant matrix. So in the vertical domain, we have the T representing time point. And we have each row as the spatial distribution of the volume. So that means we put the 3D-dimensional volume into a one-dimensional voxel, which is represented by this row. Then we have a input single matrix S, and then we are going to decompose the S into two matrices. One is called the dictionary matrix D, another is called the coefficient. So the idea is to put a sparsely constraint when we do the matrix decomposition, and the dictionary D represents the time series, that is the temporal dynamics or activities of the brain network, and coefficient matrix alpha represents the spatial distribution of those activities. So this is similar to the metric decomposition ICA, but the major difference is that we decompose the original time series into hundreds of components using the sparsity constraint. So that's the major difference. Of course, there are a lot of discussions in terms of comparison between ICA and sparse coding. So we have a couple of papers that detail such discussions. Our conclusion is that sparsity constraint might be more reasonable whenever there are significant overlaps between brain networks. So for example, spatial overlaps between these components represented by this spatial map in this figure. So if we look at the brain network template, which is represented by this group column, and the individual brain networks decomposed through sparse coding in two subjects, subject 1 and subject 2, we can find the correspondence if we use the text-based fMRI data as the input. For example, we can look at the temporal dynamics of both networks, and then we can match them together. And also we can look at the spatial maps. They typically look similar if they are in correspondence. So the problem becomes, after we decompose the fMRI input volume into like 400 brain networks in two brains, how we are going to find the correspondence between these two group of brain networks? So that's another called a pattern recognition problem. So we are going to measure temporal series and also the spatial maps. Okay. So to solve this problem, my student Yuza and other students in my group designed called a 3D CNN architecture to recognize the input brain volume to 10 typical brain networks. So in that time, we don't have sufficient neighbor data, so we start with the 10 very typical networks like this. Reference data 1, 2 through 10. So these 10 reference data networks are mostly reproducible and commonly reported in the literature. So we start with these 10 networks as the reference. And then we design the 3D dimensional convolution neural network architecture to recognize these models, to recognize these input brain networks. Okay, so if you look at the right side of this figure, you can see we have the input brain maps decomposed by the sparse coding and dictionary approach. And then we can look at the CN neighbor probability, and then we can see there are multiple labels. Of course, we rank the label. Of course, we start with the top probability, and then we can label this input volume as the label, whatever CN gives us. Okay, so we can see in this figure, the recognition performance is pretty promising. So that give us the capability of recognize at least 10 brain networks, reference state networks, from the hundreds of the decomposed brain network from either reference state or task-based fMRI. So that automate the process of this network recognition, because typically there are huge amount of variability when we deal with the decomposed brain networks. So that's why we are motivated to design an even better approach we call three-dimensional autoencoder to put all these input brain volumes or brain network volumes into an autoencoder architecture. So we have the encode on the left side and decode on the right side. We're going to encode the input volume into the feature pattern over here, and then we can do the decoding. And then based on the feature, we can do the clustering of the brain networks based on the feature between the encoder and the decoder. So we can go through the input brain network, go through the encoder and decoder, extract feature, and then we can do the reconstruction of the brain network from the input to the output through the encoded feature. So this is a simple example showing you how this whole network works from input to the output. And then once we have the recognized brain networks and the autoencoder for feature extraction, then we can cluster all these brain networks based on the features in the autoencoder. Then we can group them into more fine-grained brain network. So let me give you one example. The typical default mode network, as shown in this figure, is decomposed into 3 subtypes. So in the bottom is the typical resting state network, default mode network. And then this default mode network also exists in task-based fMRI images. So that means they are still active. So, but the pattern is different. So we can decompose, we can classify the default mode network into 3 subtypes. So that is called ICN3, ICN10, and ICN12. As you can see, the quite large variabilities. If you look into the reference state fMRI and task-based fMRI together, when we are trying to identify the default mode network from the volumes. So huge amount of variability. So we classified the original 10 reference state fMRI networks into 16 subtypes. So for example, if we look at the typical default mode network, which is RSN4, we can have 3 subtypes right now because of the variability in the different volumes, in the different task state and in different individuals. So in this sense, we have a fine granularity definition of brain networks by looking at the variability across individuals and across tasks. And then if we look at the statistics of these fine-grained brain networks across 7 human connectome project tasks and the resting state, we can see that this pattern, the ICN3 pattern, has a much larger percentage in the working memory task. And the ICN12, which is a very traditional resting state default mode network, has much higher percentage in the resting state fMRI data. So this makes a lot of sense to us. That means the default mode network, the same default mode network, has 3 subtypes in different individuals in different tasks. And then they're active, they're doing different things, so that the appearance, the spatial distribution are different. So this gives us a very good sense that brain networks are not static, they are dynamics. They have different subtypes in different cognitive tasks and in different individuals. So that means we have to be very flexible in terms of the definition or the recognition of the reference state network in the fMRI data. So that also reminds us that we need a more powerful approach to deal with definition and recognition and detection of the brain networks like default mode network. So we already deal with this very typical 10 most common brain networks in resting state and in task fMRI, but that's not sufficient. And we know that there are at least hundreds of brain networks. So in this work, my student user designed a new 3D CNN structure to recognize 144 different types of brain networks. Okay, so that means we have the input as the traditional sparse coding decomposed network, and then we are going to recognize them into one of the 144 different type of brain networks. Let's see how we're going to do that. So we start with the ABIDE-1 brain fMRI data set. So we have 178 subjects decomposed through the sparse coding, and we can have the individual function networks. So we can cluster them into 144 brain atlas group as average. You can consider that as a group average. And then we have the ABIDE-2 1099 subject fMRI data set. Then we can do the similar sparse coding and decomposition. So we have hundreds of thousands of brain network maps. So we are going to recognize them into one of the 144 brain network atlas. So this is a huge amount of data. So for example, you look at this matrix, we have around 200,000 networks times 144 atlas. So we are going to label this around 200,000 network by one of these labels. So this is a giant matrix assignment. So we are not going to do that accurately in right beginning based on the very limited training data set. So we designed and called iteratively optimized the convolutional neural network to do that. The idea is, let's do the prediction based on the weakly trained network in our previous slides, and then we can have a prediction or estimation of the label for each of the more than 200,000 networks. Then we have a good estimation. Then based on this estimation, we are going to retrain this convolutional neural networks based on the estimated labels, or we can say weakly labeled brain networks. Then we're going to iterate this whole process until converge. Okay, so that's the basic idea. So let's look at the one example. We start with the initial label brain network. We are going to do different number of iterations. In each iteration, we're going to predict the label of each network by the trained convolutional neural network. And then we're going to update the training and retrain the network based on the labeling estimation. And then we're going to iterate this whole process. So if you look at the statistics of training label distribution, we can see these 144 networks are widely distributed. Okay, so this is the percentage of the brain networks labeled by each atlas. And you can see the accuracy of this prediction is going higher and higher and higher through these iterations until it does not change anymore. Okay, so here is the distribution of the label when the network is initialized with a limited number of training samples and final label. So that means we have more and more prediction, we have more and more accurate labeling, and then we can more and more accurate training so that we can iterate the whole process until there's no change. So we can see huge amount of changes. Okay, so that means in the initial stage, the prediction is not accurate enough. But after iterations, we can get a better and better result and prediction. And it turns out that this iteration can help us to correct some wrongly labeled or weakly labeled case in the beginning. For example, this is the Atlas 7 or the brain network number 7, which is the new labeling number for the default mode network. We can see some weakly labeled cases. If the spatial overlap is below 0.2, we can say this is a weak case. But we can see the labeling by the iteratively optimized CNN is very reasonable. Here is another example, quite reasonable. And it's very interesting that some of the initially wrongly labeled brain networks with a high overlap, for example, 0.205 in this case, initial label is 3, and after iteration, the final label is 9. If you look at the distribution, you can see the final label, the 7 is, of course, is much more reasonable than the original number 3. Even the spatial overlap is higher, but the spatial distribution looks much more similar between the input and the final label, which is the default network. We can see many such examples. So that means the iteratively optimized CNN really works in terms of correcting some weakly labeled and wrongly labeled networks and change that to the correctly labeled networks. So this will help us a lot. So to confirm this the result, we visualize the brain networks in the 3D space. As you can see from the input, which is in red. The finally labeled atlas, which is the optimized, iteratively optimized network 7 in blue, I think they are more similar. So that means they really help us to identify the spatially similar patterns between brain networks at the input and the output. Okay, so that kind of confirms our conclusion that the iterative operant brain network convolution network can help us label the right network. And let's look at the big picture. So if we do the comparison between the iteratively optimal CNN model and the previous approach using the only 10 brain networks, we can see the original reference network 1 is decomposed to many different subtypes. So that means we have better understanding of the same network in different individuals and different tasks in terms of its subtypes. So the same network may have quite a different pattern for appearance. Of course, are doing different function roles, and we are able to enable this brain network with much higher accuracy by using the three-dimensional convolution network with hundreds of brain templates and with the iteratively optimized model. So that significantly advanced our capability in terms of recognized brain networks from very large fMRI data. Okay. So far we already talked a lot about the brain networks in terms of spatial overlaps. So let's look at this temporal domain. So how we are going to model the fMRI data using a multi-scale hierarchical structure based on the deep learning model. So in 2017, we worked on a called a deep convolutional autoencoder for one-dimensional fMRI time series. So idea is we have the input and output both are the original fMRI time series. We go through this called our convolutional autoencoder. So idea is we put 4 different layers to convolve the input time series and then encode the time series through this feature, and then we do the decomposition, do the deconvolution, and then we can reconstruct time series. The goal of the autoencoder is to minimize the reconstruction error by looking at the filters and do the combination of the filters so we can reconstruct the original time series perfectly. Ideally, of course, it won't be perfect. So through this deep learning model, we are able to decompose the original time series with a couple of very meaningful filters, which is the kernel of the weight in the deep learning models. So if we extract those filters or the weight of those filters, we can see the time series looks like some of the tasks in the fMRI. So for example, upside down. And then the real challenge here is how to implement this time series, these filters. So we use a visualization over here. For example, we can at least visualize the input maps and the original time series. If the overlap quite well, that means we know these filters are meaningful. So this is a layer 1, layer 2, layer 3, layer 4. We can see the original time series and the feature maps reconstructed in the model are very similar. This gives us a good confidence that the learned filters really mean something in terms of the brain activity. But this is not the quantitative evaluation yet. So we use another quantitative approach that is called fMRI filter extension. So say we have the stimulus input, so which is the stimulus design. When you do the fMRI, you have ups and downs, which is traditional block design. Then you use the hemodynamic response function to convolve the input. And then you have different theoretical models. For example, you can do the different delays, you can do anti-task, you can do integration, you can do derivative. So we end up with dozens of theoretical models. So we have the original task, we can do derivative, we can do the integration, we can do original anti-derivative and anti-integration. Then we can do different delays, like delay 3, seconds, 6 seconds, things like that. So we have dozens of understandable or interpretable filters or time series that are closely related to the input, that is the task design. So the input to the brain, you are going to follow this task. Then we look at the correlation between these theoretical models of the input and also the and its correlation between the time series or the original time series. So we can see they look quite similar, and the Pearson correlation coefficient is quite high. And we do this for different layers, layer 1, 2, 3, 4. So that means we do this correlation in different layers of the network. We can see that the Pearson correlation between the theoretical model, that is the extended task design, and the feature map look very similar. So that means most of the time series and the reconstructed theoretical model and its combination then are very similar. So that means the filters learned by the deep learning model and the combinations into the reconstruction of the time series are very similar to the original time series. So that means the deep learning model in the convolutional autoencoded really works. They really extract the meaningful patterns from the fMRI data. So we are confident to say that we are making meaningful sense out of the very large fMRI data. So we visualize the spatial location and the time series together on the brain surface. We can see that the sum of the delays going from 6 seconds to 12 seconds, they are located in different brain regions, and they look very similar because this is a visual task. Okay, we can see the delays going from one brain region to another, and the time series and the spatial location look very similar, look very reasonable. So that support our hypothesis that the deep convolution autoencoder can extract meaningful fMRI time series in a multi-scale fashion from layer 1 to 2 to 3 to 4 in different frequency domains, and represent the brain's real response to the task. Okay, so that gives us a lot of confidence in terms of using deep learning model to represent fMRI time series. So I think this paper is one of the early efforts in this direction to model fMRI time series using multi-layer deep learning models in the in this field. Then we sort of how to look at the fMRI data in the 4-dimensional in nature. So we developed a new spatial temporal convolutional deep learning model to model the time series in terms of the spatial volumes as well. So essentially the fMRI time series data is it says 4-dimensional 3-dimensional volume plus 1 time series. So that is a 4-dimensional data. How to deal with this model and extract meaningful functional brain network? This is a really huge problem in the field. So my student result, we published a paper in MICAI 2018, and then extend this paper to a journal and published in 2019. And here is the basic idea. We go from the 3D dimensional volume one by one across the time series. So let's take one volume out of this 3D space, and then use a unit structure to go from the 3D volume to a brain network. So basically, we are doing the prediction from the volumetric fMRI data to a brain network volume. For example, default mode network like this. And then we use the predicted 3D volume network to convolve with the original fMRI data, so we can have a one-dimensional time series. And then we go through the one-dimensional autoencoder we just discussed in previous slides. Then we can extract time series output from the 4-dimensional data. So let me go through this whole process one more time because it's very complex. We do the prediction of the brain volume network from the 3D original fMRI data. So we have a map. This is the convolutional. We use the map as a convolutional kernel. So we use the kernel to do the convolution on each volume in the time series, and then we have a one-dimensional time series. So this time series is considered as the correlation between the convolution kernel and the original volume. So in this sense, we extract the volume brain network and the time series or its activity at the same time. So that is the whole objective of this called spatial temporal convolutional convolutional network. Okay. So if you look at the one example, here is the ground truth. If we consider the ground truth as the sparse coding result, and then we can do the convolution, and then we can have the time series of the brain network as well. So we can see the simultaneously extract the spatial map and the time series are very similar to the sparse coding result. So that means the spatial temporal convolution network works have a comparable result to the sparse coding. And in some cases, it works much better. For example, in this case, the spatial volume over here is the spatial out of our spatial temporal CNN, and its time series is the blue one. But if you look at the sparse coding, the time series is the red one. So that means the spatial temporal CNN can extract the meaningful pattern both in the spatial domain and the temporal domain from very large data very successfully. But the sparse coding cannot do that because it influenced impact by the very large data. Okay, so that means the spatial temporal CNN works better in these cases. And if we do the theoretical comparison and statistical analysis, we can see in most cases, in many cases, the spatial temporal CNN works at least comparable or better than the sparse coding method. And in these cases, the sparse coding method will fail, but the spatial temporal CNN works. Okay, so this method for the first time gives us the capability to extract meaningful brain networks from large alpha metadata at the same time in terms of spatial and temporal domains. So that's a pretty effective approach to reconstruct brain networks. We did many different comparisons, as you can see from this paper. If you're interested, you can go to the details of the paper. Okay, so far we have talked about sparse coding and deep learning. We talked about the recognition of those spatial brain networks by the convolutional neural networks, and also model the time series in the temporal domain using convolutional autoencoder. Then we designed a spatial temporal convolutional neural network extract brain network at the same time. But so far, we have not touched the topic of a hierarchical organization of brain networks yet. So in a very recent work, my student Qingyun Dong and my student in my group designed a new volumetric sparse deep brief network to model the hierarchical brain network in the spatial domain. So the idea is, let's put the four-dimensional volume FMI data into this format. So we stretch the volumetric data into one vector and put the time series in T. So we use this four-dimensional data as the input. That's a big difference compared to our previous approach. Okay, we use the four-dimensional data as the input to this neural network, which is called volumetric sparse DBN, VSDBN. So we train the deep brief network, which is a series of stack of deep brief networks together, and so that we can model this hierarchical organization of brain network. Hierarchy means in different layers you have different spatial distribution network, and they're going higher and higher level, and they are overlapping with each other. So that means small networks compose big network in the next layer. And then if you look at the result, we can see the first layer in the VSDBN, they are pretty localized. So that means we can see 100 brain networks localized in brain regions. So that's what we're supposed to see in the DBNs and RBF, deep brief networks and RBNs. So if you look at the next layer, look at the functional network in the second layer of the DBN, debrief network, we can see they are composed from the lower layer. So that means the smaller PCF brain network regions are composed into a larger networks. Okay, so this is exactly what I expect to see. If we look at an even higher level, if we look at layer 3, we can see another 100 brain networks that is composed from the even lower networks. So let's visualize them in the brain surface. So here we can see the emotion task, the function network from the lower level was composed together into high level and high level, and the spatial map are bigger and bigger. If you look at the quantitative overlap between the function brain network in lower level and high level, you can see the huge amount of overlaps. And this overlaps going even higher and higher in the high levels. So this is the first time we are able to see the hierarchical organization of brain network in the spatial domain. So of course, we have a lot more work to do in terms of how to interpret this organization architecture of the brain network in the spatial domain and how to interpret that. So this is still ongoing work, but our initial results are very, very promising. We can see very beautiful and meaningful hierarchical organization of brain network. Okay. So in another recent work we published in April 2019, my student Chinli and other collaboration students in my lab and other collaborators designed a called DSRA, the deep sparse recurrent autoencoder. So the idea is very similar to the previous approach, but here the major difference is that we add a recurrent layer into the internal representation of the four-dimensional volumetric brain data. So again, we use the 4D time series as the input of this autoencoder. So this is input, and this output, we put the same input and output to train the network. So we go through the encoder and we have feature maps. And in the feature map over here in the middle, we have a recurrent layer over here. So we can remember, we can model the temporal dependence in the fMRI time series. And at the same time, we can model the spatial correlation. So the beauty of this DSRAE, the deep sparse recurrent autoencoder, is that we can model the spatial correlation and the temporal correlation at the same frame network. Okay, so we will be able to see the hierarchical spatial and the temporal dynamics at the same time. So let's see some of the results. So if we extract the temporal series from the autoencoder, we can see the temporal activity are very similar to the task design. And if we look at the spatial distribution, they are very similar to the spatial networks. So the difference is that we can see the spatial distribution and the temporal dynamics at the same time as showing this figure. So this is the one time point spatial distribution, and this is the temporal dynamics of the networks. So for any of the brain network extract from the DSRAE, we will be able to see the dynamic changes of the spatial distribution and the temporal activities at the same time for these dozens of brain networks encoded between the encoder and the decoder. So most dominant brain networks or brain activities in the fMRI data will be very effectively represented by these dozens of brain networks with both spatial distribution and temporal dynamics at the same time. So for the first time, we are able to extract those dominant brain activity patterns or brain networks from fMRI data very robustly and with the same spatial and temporal dynamics and with the same unified spatial temporal recurrent autoencoder. Okay, so that's the most recent work we have done for the hierarchical modeling of brain networks. So in this talk, I have touched quite a few recent publications going from 2017 to this year. So a lot of details in these publications. So I would strongly recommend to refer you to this publication if you want to look at some of the details. And so that's the end of my talk. You can visit my website for more details of the publication, my research project, and other research activities. Thank you.